binary tree. Uh, that, but this is a this binary tree, but it's not a binary search tree. For example, there is a two, then they have a two child, and then the subchild has another two child, then keep going. But there's each node has a at most maximum only the two child, or and minimum there's no child. Uh, for example, this one, it's no child, it means being called left. If is so, I mean, there is also duplicate value. For example, 2 and the root, and there's left also has a 2. So actually, this is one type of tree. But nevertheless, I mean, there's several type of binary tree. For example, usually we will use type of binary tree: full binary tree, complete binary tree. We interested those, complete binary tree, perfect binary tree. Those are very frequently used. For example, what's a full binary tree is actually, the same binary tree, but uh, actually, as you can see, I can let me just show you several picture in here, so it would be better. Let me just okay. As you can see, that's all of the node has. You know, I mean, there is a level is same, and the last one is even same. This that always has a uh, two node or no node. For example, this is no any child, that should be fine. But the root is each of them has a two child. So this is being called full binary tree. Then there is a complete. It means uh, they trying to they has the same level, but they trying to trying to arrange first in the left side. So it's a complete binary. Perfect binary trees, there is a all of the level, there is no any kind of same level they have a without any kind of sub node, a sub tree. There is a exactly same level, so it's perfect binary tree. And then balance, there's also balanced binary trees. They trying to uh, from left to right. I think from left to right, order to they trying to balance the both side of the value. So that's a different type of binary tree, um, which is helpful to get this better performance. Why? Because each time they trying to, if they're balanced, in order to get this in the one longest value, which is very easy to find. For example, if and of course there's a not been it's not easier to find, but at last, if there's a full binary tree or in the binary search tree, actually they have a able to use binary search algorithm, because the another name being called ordered tree. So let's just get familiar with some terminology. In the binary tree, for example, they have to be has let's say I just want to use some article here. For example, let's say this is the root, this is of the edge of the node. Each of the node they have a possibly subtree, and then there is, if there is no any kind of extended lift, that's being called lift. You're right. So that's a kind of terminology we will be using. Then, as you can see, there's very natural place to you can use it. As you can see, natural place to use in programming. The linked list, it is the best data structure you can represent such kind of nonlinear data structure, because as you can see, each node, then each node has in between they have a relationship. So it's the linked list is of course the better one when they represent it. There's a terminology being called height. Height is longest distance from root to left node, and also there's another terminology being called depth of node, distance between node to particular node whose the depth of to be measured. I mean, in between the two different level, not unnecessary. I mean, from the for example, they have a 10 level, but you want to trying to say this node from the second level of the node to third or fourth level of the node, how much. So basically, that's a kind of terminology you can use it to communicate it to understanding the such kind of nonlinear data structure. There is a one binary tree very useful, which is that special binary tree being called binary search tree. There is another name being called ordered tree, as you can see from the name, which has already been sorted. That's things that. Then another things that's interesting. Another thing is that there is no value duplicated. So those are the feature properties in the binary search tree. Which the first one, lab subtree node has lab subtree node has node which are only less than the k value. So it means always left side is smaller, right side bigger. All right, right subtree node has which is only greater than greater than node case. For example, as you can say, as 8 is root, and then 3 is left side. There is no 6, 7. There's all of them is smaller than root, and that's left subtree. In the right subtree, as you can see, 10, 14, 13 is always bigger than root. Each of them, each subtree is same. I mean, as you can see, even you can cut up the part of the subtree, there is a keep consistent same data structure. Each node has, and the third one is each node has distinct key. Duplicate are not allowed. So that's very interesting that, for example, there's no such thing exists. For example, 3 doesn't appear again in the other place. So what that means is this is very natural place you can use to represent the set data structure. Easier to represent, for example, any tree set, which is that definitely should be implemented by the binary search tree. So also left and the right subtree must be has binary search tree. So it means both whatever in the component of subtree is also the same binary search tree. It means same algorithm can apply for sub part. So that's a very interesting data structure. Is in the binary computer architecture. It's widely used. In terms that they use it many type of tree type. Also, they in the algorithm they also very balanced, so they will be get quicker algorithm, quicker, fast operation. They can do it. There is an operation from the operation perspective. For example, if you're trying to search, as you can see, it's a very natural place to apply that binary search. If you remember last time, last time we learned binary search all the time in one operation they will be get advanced 50% of improvement of the performance, right? Because, for example, here's if you're trying to find one, they say, seven is seven is root. You can compare it to root. If it's you're trying to find one, they should be definitely located in the left side, not in the right side. So you don't necessarily to check 9 and 14s, but only focused on those subtraits. So it means that should be more faster than any algorithm, and because they used it. First of all, this has already been ordered, but so this is a natural place to we can apply binary search tree. So as you can see, that's a linear data structure. We can put it as a, it's non-linear data structure. We can put it as a linear data structure. You can able to more linear way to analyze. For example, here's 5 is for example, hold on a second. This is middle. This is root, and then as you can see, in the middle is 5. So you compare to 5, it should be hold on a second. They trying to find which element. In this example, trying to find the 9, right? In this example, trying to find 9, first what they try to find the binary search, which is middle. Then they say, okay, that's we need to start from the left side. So what's left side is that one. Then you just need to just 3 steps to complete this. You find 9. So that's interesting. And then here's a you can see that definition, and as well as from different perspective, the comparison of in order to enhance your understanding of those concepts in order to apply those knowledge. For example, here's from how is different of definition from the structure perspective, operation performance perspective, as well as type. You can able to compare the terminology binary tree and the binary search tree. So actually, the binary search tree is a special type binary tree, but this is well organized. It means actually already been organized. Left side is always smaller, the right side is bigger than root. And then but binary tree more general, they only have a one child, or one no child, or 2 child. There's no such a thing exists that one node has a 3 child. If why? Because actually it's not useful from our computer architecture, because our computer architecture only able to represent two variable, right? 0 and 1. So it's not useful to, if there is a child should be same node has a 3 child, it's not proper place to proper data structure we can able to compute. So yeah, from the definition that would be, yeah, a binary search is organized binary tree with a structure organized of node. Each subtree must also be to be particular structure. It means they will be very well organized. Left side, right side. Right side is bigger, left side is smaller. Yeah. There is no required any organization, so it means kind of general definition. There is a big category, but this is that binary search is special category. We just only interested the binary type. Not only binary type. Actually, we trying to get this more balanced the data structure in order to get this better performance. Operation, you just need to do, you just need to just usual way we can perform the insertion traverse operation, but this is a not guarantee the better performance. But if we use the binary search tree, they will be most efficient, the insertion deletion as well as the fast finding operation can be done with the binary search tree. And the type of binary tree you can find, complete binary tree, full binary tree, extend binary tree. There is also as well. And most popular implementation of the binary search is AVL tree. Yeah, that's and the Tango tree. Those are kind of application, or say library already used it in the binary search tree. So that's kind of first step. How's the binary tree look like? And then yeah, that's ordered binary tree. As I said, binary search tree is another name called ordered binary tree. Another attribute is non-duplicated. So these two attributes give a proper properties, get advanced without they doing the operation. All right. So then property binary tree, as we explained here, is four type. I think yeah, it's understandable. Left tree is always smaller than right tree. I mean, left tree is always, you can put this the left tree and the smaller one, and smaller than root. Right tree is bigger than root, and as well as keep recursively keep such kind of data structure. And then the third one is no duplicate value exists in this binary search tree. Left and right tree is almost binary search tree. It means same data structure. In the keep continue growing in the sub-binary tree. So it means we can able to easily to apply the recursive approach as well, no problem for an implementation perspective. Yeah, wondering before that we implement. Our next question is, of course, before we needed to make a conclusion, but after that we are going to how to implement in the coding type, right? So it's also important. But before that, there is another a definition. Now is the kind of what's different between the BT and then binary tree and the binary search tree. Definition is binary tree is the non-linear data structure. Both are same, right? But they can it's more general way they can use zero or no maximum is two children. Binary search tree and instead of binary search tree is the ordered binary tree. It's kind of special, right, compared to BT. And then structure is the binary tree that first node and the topmost node known as the root. Each node in binary trees contained left pointer and the right pointer, and the left pointer contained the address of the left subtree, whereas the right, I mean, that's kind of linked list, and then this linked list is double linked list. Is better to represent the binary tree. From the coding perspective. Binary search is one of the type of the binary tree that has value of the all the node in the left subtree less or equal to the root node, and then value of the all the node of the right subtree is greater than or equal to value of the root. So that's also definition one. When you initialize binary search in the coding, you have to initialize such a way that create each node would be placed proper place, because this is a When you create it, actually they already beginning to generate the binary searches. So that's the reason. In terms that the operation, it's very important because our motivation is use those data structure to complete certain tasks. So we must be find, we must be placed, we must be insert, we must be delete, and much reversal is kind of find, right, the terminology. And then binary searches provide the most fast data structure, fast performance they provided, because first of all, this is ordered, so we can able to use binary searching, which is that the most fast algorithm exists in the binary architecture computer, which is that we use it everyday life. So that's very perfect data structure that founded in the binary data structure. Then same time, because the level, so the performance actually they can find or insert or delete, they can able to, let's say, login time complexity, finding the any element, so which is that better performance they can provide it. That's same implementation. If you're interested, see more details, you can open it. Yeah, you can able to see more details. You can able to read it. Now, I think there is a thing that how next question is how we can implement it, right? How we can implement in the computer, how we can represent it, right? So that's the reason. First of all, of course, what kind of data structure is proper to represent a tree, binary tree, which is that double linked list. As you can see, that's k, and then there is a value k, then also has a two pointer, one's left, one's right. So when you create a new node, you needed to add one, and then create a new node, right? So first of all, the item you can keep. I mean, this is a this value that then left and the right is at the first is null. So because you just need to at first there is nothing is created, that should be new node. When they use it insert, when they doing the operation of insert, of course you have to give them node, then as well as the k. So if the node is null, means you just need to create it, which is that you just create beginning to create, which is you just need to call this the function. But if the k itself smaller than a certain node of the k, then you needed to keep find which one is a smaller one. So you needed to recursively update the value, right? So for example, here's if the k is k, the trying to k, the is try to compute in the beginning of the root maybe, then they say what's the value. It is smaller, when you needed to, okay, let's go back to insert in left side. So you needed to maybe in the first level still think that this case didn't found and the left, so you need to keep checking, keep finding the smallest value, then finally they will be located insert in the proper place. But if it is the case bigger than a certain node, it means that the place should be put it in the right place. So that's the reason, that's algorithm actually make this data structure, make this tree, make the binary tree, order the uh, order the uh, order the data structure. And then search is also uh, same. As you can see, because it's natural place, you can find first the value, compare the root, then they say where is the my value. If this is the smaller, then go to the left side. If it is a bigger, then go to the right side of the subtree. At the same time, this is a you need to compare the value. It's not the same. Then you need to keep continue to find the smaller value, which is find exactly the value we're trying to find. Otherwise, they say, okay, you can't find. So that's also the three, insertion operation and the search operation. And then here's no delayed operation. But probably there is also has another article which is demonstrate the delayed operation. For example, it should be here's a delayed operation. How does it look like? Of course, definition of the node. Of course, creating initialize the any new node. Insert if it is null, just I mean that's in order function, not insert, of course. That's for the trying to visualize perspective. Insert the same, you already explained it, but we interested in not delayed. Delayed is if it is the null, just return the root. It means there is no value existed. If there is a find it left, then they just okay, they needed to return. But if the value, certain value is smaller than k of the row, k of the node, it means you needed to finding the value, then going to delete, and they will be located in the right, located in the left side. So that's the reason the recursive process will become, continued to update the pointer, left pointer. And then if it is the value the bigger than root value, then should be definitely the value should be located in the right side of subtree. Then you need to keep continue to recursively call the same function, but you need to update the right side of the pointer. So yeah, they need to keep continue. If this is one, if there is a one child's null, then yeah, they definitely make it release. Otherwise, right child, make it null, then you need to make it relate this value. If both child existed, then you needed to make it the success parent to root. Yeah. So basically, that one, they will be, when you delete it, after that you needed to keep this balance then in order to get this better performance. So that's yeah, operation that you can complete it. So basically, the time complexity of depend on height. So if the height is depend on the binary search tree, if it is the very balanced, this is more shorter. If there's more shorter, you will be get better performance. So OH, actually the H itself is depend on binary search, value binary search should be login time. So this is a kind of you will be get OH if H is fixed. I mean the level is usually not, yeah. So it should be you will be get much faster performance. I mean it's not. I mean it should be. Uh, you needed to compare to, for example, n, right, and then age. For example, in between how much the, for example, n is should be million, then age should be login time of the n. So that's the reason BST is actually the login time performance. So they actually depend on age because they mostly balance the data structure, balance the binary tree. All right. So that's a kind of a little bit explanation of the how's delayed operation of in the delayed operation in the BST as well as insertion operation BST. You can reference those articles. You can check it after that. Wondering maybe what kind of application probably used the BST. Actually, in the library, for example, in the Java, for example, CHISET, CHIMAP, HashMap, they actually already used binary search tree. So it means if you use the CHISET, CHIMAP, HashMap, actually already guarantee that you will be get login time complexity. I mean better performance you will be you will be get. Then also another example application is in the Linux kernel. File memory mapping is another example. And the key means clustering is in the machine learning. Actually used machine learning of type of machine learning algorithm, which is actually used the binary search tree. Now, as we remember, there is in the binary search trees one type of binary search tree is actually mostly widely used. It is AVL. So AVL is one type of application which is when they doing the operation, for example, anything you can done, any operation any operation you handle in the binary search tree, for example, any operation, for example, let's say insert or delete. After what will be happen is after that insert and delete, you will be destroy the balance. What's the destroyed balance is actually is not been sorted data structure. If not been balanced, that means you are not after that you are not guaranteed to get better performance. So what you're doing is if after that accomplished any certain operation, if the data structure itself is self-balanced, immediately self-balanced process been activated, or it would be better to apply for. So that's the reason AVLs actually provide such kind of balanced algorithm. So what's behind sense of how they next question is how they get balanced binary tree, right? So actually the AVL is trying to let me find AVL operation. AVL is actually trying to for example, you delete one value for each, right? After that, definitely they will be, after the one should be linked with the value, right? Or then, for example, here's you needed to replace with the 11, then should be fine. But if there's something's already destroyed this balanced order, then you need to rebalance. What they're doing is actually they're trying to find the smallest value, then rotate it. Then finally they can able to balance it. Then should be keep this AVL is more better performance. Compared to AVL, there is another data structure being called Lec4 tree. I mean that should be BRT, red black tree, which is kind of not tend to optimize the operation. They just trying to balance the operation. So they both are different kind of philosophy. One is that trying to absolutely balanced, but red black chick trying to trying to average balance. What does means is, for example, if uh, absolute balance, they will spend too much power, then actually you will be lose the performance. Then in that case, red black cheese give the better performance. But if this is height is not too much too deep, then uh, AVL is better choice. So depend on the case. um, Maybe you can use red lecture or AVL, depending on the situation. So both are uh, trying to balance after that certain operation is broke the balance. Then they trying to rebalance again. So that's lecture and the AVL tree certain operation with the trying to keep this whole algorithm more useful. Compared to AVL and PAT, there is a kind of comparison graphic, which is that strictly highly balanced. She is AVL, high balanced, means always trying to balance the high. And then BSC is roughly balanced, that means they just only compared one time. So it is not optimal, but very fast. Com Comparatively complex implementation, and then PRT is implementation. Take more processing for balancing for AVL, but less time for do such kind of operation. Certain operations faster because of the height balanced. Certain operation is comparatively slow because not being optimal. Insert deletion operation is slow because after that you needed to you needed to rebalance completely. But this one insert deletion is fast because they just need to only do one more operation, try to just one more operation. So that's the reason fast, but it's not optimal. Yeah, so balance is factors associated with node. There is no balance factors node. Use the database, application, and AVL4 use the database, and BRT use the any language library you can find it. So I think that's as you can see, that's the time for end of the lesson. I'm trying to recover again. So actually, today we give them one example of the binary tree, then also recommend to one binary tree, special binary tree being called binary search tree. Give them they actually give us to better performance of the option of data structure because this one is most balanced binary tree they can able to use it. But then after that, of course, there should be we concerning from the usability or application perspective, how would be influenced it, right? So when they doing this, when they doing a certain operation, for example, insert or delete, they will be definitely broken the data structure itself. So it's not keep this, keep the same as before via BSD. So there is a two that algorithm, AVL and the BRT, actually using the BSD to keep balanced always after that the certain operation completed. For example, they broke insert, after that insert, they will be keep balanced. After that delete, they will be keep balanced. So the two of them is the two different kind of philosophy behind. One is trying to AVL is trying to completely balance again, but BRT is just balanced the two more times. So that's the reason BRT, red black tree. They just using, if there is a deleted, just one switch in one time. But it's not optimal, by the way, but kind of, but it should be more a little bit faster. So that's the whole of the today's lesson. It is kind of nonlinear example of related to linear data structure lesson for today. I hope this should be makes sense for understanding. Using those after that lesson, maybe using those related to articles and then some coding analyze. You can, yeah. I hopefully it should be useful. Yeah. Any question?
No
No
questions.
questions.